Okay, we are here and ready for 9.3. We're going to look at our circles in the coordinate plane. So we have kind of skipped around and we've looked at circles, we've looked at parts of circles, we have talked about the chords, the diameters, the radii. We've calculated area, we've calculated circumference, we've even jumped ahead and looked at arc length and sector area. But what we have not looked at so far is an equation for a circle or how to graph a circle in the coordinate plane and what that equation does as we move that circle, whether we're dilating it, translating it, and reflections and rotations aren't really going to be as obvious with circles because of the nature of their shape, but we can still manipulate them in our coordinate plane as we could with anything else. If we don't know how to put them into the coordinate plane though, we are going to run into some trouble. So here, as we get started, when a circle is centered at the origin, again, that is going to be important for us to start with. So if we're centered at the origin of our coordinate plane, our equation is simply x squared plus y squared equals r squared, where r is the radius of our circle. Now this equation should look really familiar if I rewrite it. Now notice that x squared and y squared could be replaced with, let's say, a squared and b squared, and then our r squared could be our c squared. So a lot of similar connections. That Pythagorean theorem still creeps up. So our coordinate equation for a circle is the same as our Pythagorean theorem. Now this is important to keep separated on one hand because our Pythagorean theorem allows us to solve for an unknown side, such as a leg, A or B, or a hypotenuse, C. Now, our circle equation is for graphing purposes in most cases. So in this case, x and y are just 2 points, x and y. R is our radius. It is connected to the Pythagorean theorem, and Pythagorean theorems are for triangles. So how they're connected is a little bit messier, but it deals with the distance formula. And so if we remember that our distance formula was based off of the Pythagorean theorem as well, because all we did was our distance was essentially our hypotenuse between 2 points. So we changed our c value to d for distance, and we took the square root. Now our legs turned into horizontal and vertical distances. Okay, if I take something like this, and let's just pick some point R, say that that's R, I would go up and down to find maybe my B or A. Left and right would give me my other one, so that's B. And then here, oh, I used the wrong coloring, but the distance from the center is R. That's my distance out to that point. So that's where our circle formula comes from, the Pythagorean theorem. Okay. Our hypotenuse is our radius at any given point. X and Y are the legs that we would get if we came straight down and straight over. or straight over and then straight down. If we create a triangle at those points, including the center. So again, there's the connection. I'm not necessarily testing you on that direct connection, but if you recognize the patterns and are trying to see where they come from, or if you see later that there is that connection to the distance formula in our equation for a circle, it's all coming back to that Pythagorean theorem. Okay, so let's look at this. We want to find the equation of the circle pictured below, and we want to assume that each unit shown is 1 unit. So it is going to take some looking at what each unit is and trying to count. So I'm going to take my red pen here. It's a little bit finer of a point. And because I've already marked up to the right, I'm going to go to the left. I'm going to see this is 1, 2, 3, 4 units. Now it is a circle, so let's hope that that radius is the same. If I go up, I've got 1, 2, 3. I hit it 4. If I go down, 1, 2, 3, and 4. So my radius is 4. When we're trying to find our radius in the coordinate plane, always count from the center up, down, left, or right along horizontal paths, unless you were given something else. So I'm just jotting that down as a reminder, since I know some people don't actually watch these videos or watch them fully or listen to them slowly, which is fine, but we need to make sure we have it. To count that radius, start from the center of the circle, count up, down, left, or right, horizontal or vertical segments. Here our radius is 4. Now, our circle is centered at the origin. If our circle is centered at the origin, then we can go straight to x squared plus y squared equals, centered at the origin, x squared plus y squared. Now this side again is our radius squared. We know our radius was 4, and we need to square that. Now here's where some of us still get a little bit lazy. If we're looking for the equation of a circle, we want to calculate whatever we can calculate, which means we need to evaluate 4 squared. So our solution is x squared plus y squared equals 16. Now, since it is not always possible to have our circle centered at the origin, we have developed what is called our standard equation of a circle. And oftentimes we'll just say standard form. So our standard form or standard of equation of a circle now has a center of hk. It's no longer the origin or 0, 0, and we still have radius r. But now our equation is x minus h squared plus y minus k squared equals r squared. And our changes deal with our center. H, K. Otherwise, it was the same thing we had before, x squared, except now we're subtracting the x value of our center. y squared, but now we're going to subtract the y value of our center equal to r squared. Now here, same kind of idea. I drew my triangle in this picture. Now when we do this triangle, this distance isn't just counting from 0. It's just not x units and y units. It's x units over, because if we come straight down, this is x. And if I come straight down from here, this is h. If I were to come straight across, this is y. And straight across here is k. Again, our difference, x minus h, tells me that distance. Y minus k tells me that distance. That's where I'm getting those legs. R is my radius. Still comes back to the Pythagorean theorem or the distance formula. Okay. Now, what this is really doing is telling me how to get there. The subtraction comes in here from our distance formula and our Pythagorean theorem, our ruler postulate. It can be messy. Part of this helps if it goes the opposite direction. So negative usually means I'm going left or down, but when it's inside of our circle, our minus means we're going right or up. So kind of backwards of what we may have learned before. So part of what we're going to do is write our standard equation. So we want to start by deciding, is our circle centered at the origin or is it centered somewhere else? So I'm going to go through and I'm just going to highlight where the centers are. So in this first one, I am centered at the origin. The second one, my center is at 1, 4. Well, this next one, it is clearly not at the origin. So we're going to talk about how to find that center here in just a moment. And then the next page will have some other examples or problems. So if it's centered at the origin, again, we start with x squared plus y squared, and all we're concerned with now is that radius. So let's go ahead and highlight our radius. Our radius is 3.5. This one does not give me a radius. This one I'm going to have to find my own radius. So this 3.5 squared which means x squared plus y squared equals, this is some 9.25 maybe? Nope, I am not right there. Helps if I get the right answer. 12.25. Glad I double checked with my calculator. So that would be my equation of that circle. Now, if I wanted to work this backwards to find the radius, I need to remember this is radius squared. Just like this would be hypotenuse squared if I'm looking at a right triangle. Okay. Now, here in B, we're looking at a circle with a center of 1, 4, and it has a point on the circle of 4, 1, which that means I need to find the distance between those 2 points to find the radius. So my radius is the distance, or square root of 4 minus 1 squared plus 1 minus 4 squared. And that's my change in x squared plus my change in y squared. Essentially what I would have up here. So 4 minus 1 is 3. 3 squared is 9. 1 minus 4 is negative 3. Negative 3 squared is 9. So this is the square root of 2 times 9. 9 plus 9 is 2 times 9, which is 3 root 2. So I have my radius, I have my center. I'm going to need my radius squared. If I need my radius squared, did I need to find my radius? Absolutely not. If I needed my radius squared, I could have squared both of these from the beginning. And that would have just been 2 times 9, or 18. And if I square this again, I'm going to have 3 times 3 or 9. Square root of 2 times the square root of 2 is 2. 2 times 9 is 18. It's going to come right back to that. But I digress. We're centering at 1,4. So this is my H, and this is my K. So my formula, X minus H squared plus Y minus K squared equals R squared. So there is the equation of my circle. Well, this one has those extra steps, but it's very doable. For C, if we're given the graph, we have to find the center. Now, finding the center for some of us is super simple. It's very visual. For others, it's not as much. But we have to find essentially our maximums and minimums. How far up and down does our circle go? How far left and right does our circle go? And that's really going to be what helps us find those centers. And those maximums and minimums tend to help. So maximums and minimums, if I go all the way to the left, I'm going to go for essentially where's that tangent line, or can I box in this circle? So I come all the way down here to -8. Furthest right is 1. Oh, sorry, that's -9. -9, -1. Then, if I do the same thing top and bottom, I'm hitting 8 at the top and 0 at the bottom. Again, that means that each diameter runs through those points. So I can kind of find where those are going to intersect. Find where those are tangent to my circles and draw my diameters. Okay, some of you don't need that extra step. But if you struggle with the visual side, try to box it in. So here my center is at the point -5, 4. My radius, now I could take this total difference, 8 minus 0, which is the diameter, and divide by 2. -9 minus -1 and divide by 2. Or once I find the center, I can do the counting I mentioned up at the top. I can say it's 1, 2, 3, 4. Or 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Either way, my radius is 4, which means my radius squared is 16. Okay. So if I'm going to plug this into the formula of my circle, H and K. And center is H and K, R squared is R squared. So if X minus, well, subtracting a negative is plus 5. Forgot that that's quantity squared. And Y minus my positive K squared equals my r squared. So that is the equation of this circle pictured. Okay. Now, sometimes we're going to take it straight from an equation. In this case, we have the formula. We have to decide if it's written in the proper format. Okay. So in this format, we have x minus h squared, y minus k squared, r squared. Okay. So it looks like we're in the right format. Okay. We do need to make sure we're adding in here, which we are. Everything's being squared, everything looks good. The only thing that's really different are these signs. So this is plus 3. Our formula says minus 3. All that means is that this sign is going to be negative. So it's negative 3, and this one will be negative 11. Now because this says 196 squared, our radius is 196. If it didn't have the exponent of 2, we would need to take the square root here. So we do have to pay attention. It's going to be given to us in both ways. Some are there to trick us. They're designed to see if we're paying attention. So pay attention. Okay. Now, the standard form is also known as the conic form. So that's there if you see it maybe on Delta Math, maybe on SATs, maybe when you move on to pre-calculus or calculus, textbooks may change. Again, we call that the standard form or the conic form, but there is also something called the general form. The general form and standard form sound almost like they should be interchangeable, and in some ways they are, but not as forms. So general form is going to be more like a quadratic. Ax squared plus by squared plus cx plus dy plus f equals 0. Now, if we're in that form, we have to use our algebraic technique called completing the square to rewrite our equation into conic form. Now, that's if we want to be able to quickly and easily identify what our center is and what our radius is without using high-powered technology such as Desmos. And if you have the opportunity to graph in Desmos, Desmos will recognize your conic form and your general form and your standard form and any other form of the circle that you try to plug in. It will do that. But when you are not given access to it, which may happen, we need to know how to redo it. So we have our general form. We want to find our center and our radius. We are going to need to complete the square. Completing the square is not difficult, but it is weird, and it is one that often causes challenges. So I know some of you learn better faster, and I tend to slow down when I think it's important. So if you do better faster, keep watching it fast, but if needed, repeat this. Okay. So I'm going to change the way I write this. Let's see if I can tilt this here. So I'm going to take my x squared, but then I'm going to take my negative 2x, and then I'm going to put a blank. And then I'm going to take my plus y squared and my plus 6y, and then a blank. Then this minus 6, I'm going to add to the other side. So instead of minus 6 on the left, I have positive 6 on the right. If you learned how to Complete the square when you learn factoring in algebra and you remember it. This should look familiar. Not everybody learns how to complete the square, or it's not always a top goal. So it does look a little weird. So what I'm going to do here, I'm going to do two different colors, one for my x terms and one for my y terms. But to complete the square, we take this middle term here. We take that, I'm going to take -2. We divide it by 2, and then we square it. And we put that right here, and then right here. Again, what we add to one side of the equation, we have to add to both. So -2 over 2 is -1. -1 squared is +1. So I'm going to add 1 to both sides. And I'm going to do the same thing right here. I have 6. Always divide by 2 and square. The only number that changes here is that top number. And then that goes here and here. So 6 divided by 2 is 3. 3 squared is 9. Now, the reason we do this is because now we should have some perfect square trinomials. I'm going to change the curve of this so I have a little more space to work. Completing the square gives us these perfect square binomials, which means that now it should be easier to factor. So x squared minus 2x plus 1 means that this is going to be x minus 1 quantity squared. And now I know this has to be a -1 because my middle term is negative. But then my last term becomes positive, so when I FOIL this back out, -1 times -1 is +1. Then I have to add to that what happens with the y's. Now, if you do have coefficients on your x's and y's, after you do some of this, you might see after or before. See if you can factor out a GCF first. See if you can pull that out. Otherwise, you're simplifying. This might not be as simple, but you shouldn't have too much trouble. Okay, this is a perfect square. Its square root is 3. 3 plus 3 is 6. The only other alternative would be if this was negative, and this is positive, and then we would be looking at -3's. But because both are positive, this is going to be +3. So this is y plus 3 quantity squared. Essentially, it's whatever this inside parentheses is before you square it. Again, before we square it, it comes down in here. Then this last side is the sum. So I have to make sure I've added that 1 and I've added that 9 to the 6 I brought over. So this equals 16. So now when I'm looking for the center, this is my h, this is my k, and this is my r squared. I have to remember that's r squared and not r. So h is 1. The formula is minus h, so it's +1. Minus k, and I have a +3, so this will be a -3. And I want the radius, this is r squared, so I need the square root. My radius is 4. So if it's in general form, more than likely you're going to have to complete the square. Now, our last one is a word problem. Circles and their equations do get used a lot to find something like epicenters. They can be used to trace cell phone calls. It's often, as silly as it may sound, used when we are trying to triangulate something. So if you watch cop shows or anything like that, and you've heard them talking about tracing those cell phone numbers, they need to triangulate where it was. This is it's very similar to what we're doing in this word problem. Well, this word problem is looking for an epicenter of an earthquake, same concept. So we have an epicenter of an earthquake that is 10 miles away from the point -3, -1. So they've taken our earthquake information and they've plotted it on a coordinate plane. And that allows them to get some of this information together. So let's see what we can do. If I have one earthquake 10 miles from -1, -3, and then I have one, or it's the same earthquake, but I record it 2 miles away from 5-3, and then I record that earthquake again 5 miles from 2-9. So we've recorded it from 3 different locations. Let me get that a little less blurry. 3 different locations. We know where the locations are. We know how far the locations are from the epicenter, which is usually determined by the size of the waves or something similar. And now, with that information, we're going to determine the coordinates of the epicenter. Now, if we have put our whole map on top of a coordinate plane, this would tell us exactly where on the map that epicenter fell. Now, what we may not know is that the distances 10 miles, 2 miles, and 5 miles are the radii. So this is radius 1, radius 2, radius 3. The others are the centers, or H and K. So let's do circle 1. We are going to do our x minus h, and that's a negative, so plus 1 squared, plus y minus -3 squared was our radius squared. 10 squared is 100. Then let's go circle 2. It is x minus h, this time h is positive, plus y minus k, again k is positive this time, equals our radius of 2 squared, so that equals 4. And then the last one that they gave us here, third circle, were 2, 9. So x minus 2 plus y minus 9, and our radius is 5. 5 squared is 25. Now to find the coordinates of the epicenters, we want to see where all of these meet up. So we really want to graph them. And to graph them, I'm going to tell you to graph them on Desmos. Now on Desmos, I don't even know what that is. On Desmos. Now we're going to graph on Desmos because graphing lines is one thing. Graphing circles, trying to get it to be a perfect circle and match up with coordinates is really messy. Unless you are really good at drawing circles, especially without a compass, this is going to be a challenge. So just use Desmos at this point. And I'm going to pull that up. Set that right here. Then Desmos, we can type it in as we see it. So x plus 1. Oops, I didn't put my 1 in there. Squared. Plus y plus 3 squared equals 100. Okay. And actually, I'm going to go ahead and pause and finish typing these in so I save you just a little bit of time. Okay, so I went ahead and I graphed all of them. I even changed the colors to match the best I could. They didn't have a pink, so I went with red there. But the orange one matches our first circle, red matches our second or pink, and the green matches our green. And if you do a quick double check, I should have those all typed in correctly. It looks good. So I'm going to hide this for now. I'm going to hide that, and I'm going to pull this up. Now, if I zoom back in here, what I see is that those 3 circles are overlapping. Again, my first circle is this really big one. I had a 10-mile radius from that center where I was able to pick up on the earthquake. Then that second center only had a 2-mile radius, so it didn't pick up for very far. The third one had a 5-mile radius, a little bit larger, but it picked up. To find that epicenter, I have to find where all 3 of these circles overlapped. Since all 3 of them picked up on the earthquake, it has to be something that all 3 of them match up. So like with Desmos, if I click, it's going to hover on some point. So if I hover over here, that could have been the epicenter if I only had data for 2 of the circles, because they overlap. And anything in between the overlap of those 2 circles, such as a Venn diagram, could have worked as well. But again, this would have worked for those 2 circles or anything in between. It's the reason we have 3 circles and we call it triangulating that really matters to finding that exact epicenter. Once we have 3 of them, our chances of having multiple places in common start to dwindle. There is only that one point where all 3 of them are going to overlap in this case, and that's at the point 55. So the epicenter of our earthquake is at the point 55. So let's go ahead and do that. So the epicenter is the point of intersection of all 3 circles, and that is at the point 55. So we kind of wrap this one up. Hopefully it's still recording properly since I took that down, and I'm going to try to keep that in a little corner over here maybe. I'm always worried that it's going to start recording something it shouldn't when it moves on me, so let's just keep that down here in the corner as I wrap this up. So again, this is one of the longest videos, but it is one of the most involved sections, and you will still have access to watch this at twice the speed. There will be a few questions on your final over this material, as well as your final skills check if I decide to move forward with the skills check. So make sure you are getting some sort of understanding of these equations. They will follow you forward. Understanding circle equations will also show up on things like your SATs. So even if you don't move forward with other classes that go into circles, this is something you will be tested over later on. As always, if you have questions, ask. We're just a few days left in this year, but there's still time to learn and do better and improve your understanding.